Now we're going to learn how to write these balanced chemical equations without drawing pictures for everything. So here are the instructions. We'll go through this and then we'll do several examples. The first step is to write a skeletal equation, just kind of a rough draft of your equation, using the correct chemical formulas. So in these examples, you're going to be given a sentence with the names of the chemicals, and you'll have to figure out what their formulas are. Other times you may be given the skeletal formula, or you may be given the formulas for the reactants and products. But whatever you're starting with in this first step, you need to figure out what are the correct chemical formulas for the reactants and products. And then we start balancing it. And this technique is called balancing by inspection, and it's sort of a trial and error method. And so there's no one best way to do balancing. Okay, it's, what works for some equations doesn't necessarily work real well for the other. But here's a couple of guidelines. If an element occurs in only one compound on each side of the arrow, balance that one first. And if there's more than one of those, start with the metals before the nonmetals. That's just kind of a guideline, not a hard and fast rule. The third one is also a guideline. If an element occurs as a free element on either side of the chemical equation, save that one for last. Because when you adjust that one, you're not going to mess up anything else, and we'll see an example of that. So in that first example that we had oxygen, O2, on the left side. That's an element by itself. When you're balancing, you want to save those for the end. It'll just be easier that way. Number 4, if the balanced equation contains coefficients that are fractions, you need to multiply them. You multiply the whole equation by an appropriate factor to get rid of the fractions. And I'll show you that we can avoid having fractions in our equations. But some of you may have learned how to do it with fractions before, and if you do that, that's fine. But I have a friend who teaches middle school math, and she tells her students that fractions is the F word. And for some of you, I think you would probably agree with that. So we can actually avoid fractions. But if you have fractions in your equation, you got to get rid of them. And then at the very end, important step, check to make sure that it's balanced on each side. And after you've maybe spent 10 minutes balancing an equation, this is the last thing you want to do, is go back and look at it again. But do it anyway. If you check your work, you're going to get the answers correct a lot more often than if you don't check your work. And here are 2 very important things. Do change the coefficients to balance the chemical equations. Those are the large numbers in front of the chemical formulas. Do not change the subscripts. Students like to do that because it's easy. It's easy, but it's wrong, okay? And easy's not good if it's wrong. I'm all for easy if you get the right answer, but that's not going to get you where you want to be. So those are the rules. Let's do some examples. So these are all going to be sentences with names of elements and compounds, and so then we have to write the formulas, and so this is also going to give us some practice from Chapter 5, the nomenclature stuff. So here we're asked to write a balanced chemical equation for the reaction between solid copper and solid sulfur to form solid copper 1 sulfide. And so when we look at this, we see that they're naming off a bunch of things, and when we see this to form, when you see to form or to produce, that's where the arrow goes. So the things that are listed before that are the reactants, and to form or to produce or to make is the arrow, and then anything listed after is the products. So the first thing we have to do is figure out what these formulas are. So solid copper. Okay, that is just the element copper. Copper has the symbol Cu. Whenever you're writing an element, ask yourself, is that one of the 7 diatomic elements? No, it's not. We're going to write our state symbols in here just because they're giving us the states, so we don't even have to think about it too much. So solid copper is copper with an S in parentheses afterwards. So that's one of the reactants, and that reacts with solid sulfur. I'm going to leave a space there in case I need to put a coefficient in. If you write them all scrammed up close together, then you're going to have a mess on your hands. So sulfur has the element symbol S, and then you ask yourself, is that one of the 7 diatomic elements? And the answer is no. So that's just S, and that has a lowercase s in parentheses afterwards. Then we have the arrow, and this is forming solid copper 1 sulfide. Okay, so now we're going to have to write a formula. Copper 1, we see that Roman numeral, and that's our big clue. This is an ionic compound. We have to write the formulas for the ions first. So copper 1 is Cu plus. The Roman numeral 1 tells us the sign, the charge on the ion. So it's Cu plus. And sulfide is sulfur, and we look at the periodic table and we count to the left from the noble gases are 0. Chlorine is -1, sulfur is -2, so this is 2 minus. We look at those charges, you can do the crisscross thing, and you come up with Cu2S. And we're told that it is a solid, so we put an S afterwards. Okay, so that part is really a review of Chapter 5. Now we're going to balance the equation. This one is pretty simple, which is, why we're starting out with it. The instructions gave you some guidelines, and those are good. A lot of times it works out to just start on the left and work your way to the right. So copper shows up first. Let's see if copper is balanced. How many copper atoms are on the left side of the arrow? 1. And how many are on the right side? 2. So that's not the same. We have to make them the same. Well, we're going to add things. We're not going to take things away, and we can't change subscripts. So I'm going to put a 2 here. Now I have 2 copper atoms on the left, and I still have 2 on the right. See that? Now let's look at the sulfur. How many sulfur atoms on the left? Just the 1. And how many on the right? Just 1. So that's balanced. And there, that's done. That is the balanced chemical equation. Some of them are like that. They're really easy. And some of them are not so easy. Any questions about that one? We'll do another one. Question?
How did we get the 2 for copper?
How did we get the 2 for copper? We had 1 copper on the left side, and there were 2 on the right because the formula was Cu2.
Yes.
And so we need to make there be 2 coppers on the left. So we're going to put in the equation 2 Cu so that we can balance it. And it's not that we're adding copper atoms to the reaction. We're not affecting the reaction. We're adjusting our description of the reaction to match what's actually happening. So here's a second example. Write a balanced equation for the reaction between sulfur dioxide gas and oxygen gas to form sulfur trioxide gas. Again, we see that to form, which divides the reactants from the products. So we've got sulfur dioxide and we've got oxygen gas. And what are the formulas for those? Well, we have to recognize what kind of compounds they are. Sulfur dioxide. Sulfur's a nonmetal, oxygen's a nonmetal. This is one of those covalent compounds. Sulfur dioxide is just SO2. The prefix tells us how many oxygens. The implied prefix of mono on the sulfur tells us there's only 1 sulfur. Remember, we don't use mono on the first element. There's no way to figure this out based on charges because both of these form -2 ions. And there's no way you can combine -2 and -2 to get 0. It's just not going to happen. And this is a gas, so we'll put G after it. This is going to react with oxygen gas. So the symbol for oxygen is O. And then we have to ask ourselves, because this is an element by itself, is oxygen one of the 7 diatomic elements?
Yes.
It is. Horses need oats. Oats, O, oxygen. So this formula is O2, and that's also a gas. Then we have an arrow, and then we've got sulfur trioxide. Well, that's real similar to sulfur dioxide. It's just going to be sulfur with 3 oxygens, and again, it's a gas. So there's the first step, is getting the correct formulas. If you're balancing an equation and you go round and round and you decide that, you know what, it's not possible to balance this thing, examine your formulas. Because if you have a formula wrong, it may be impossible to balance. So now let's inspect this. Here's a situation where we have an element by itself, and so the guideline said save that one for last. We also have sulfur appearing in only one compound on each side, and that would be another indication that we should start with sulfur. So let's look at how many sulfurs there are. I'm going to show you a little technique that some of you may like, just kind of keeping a tally down below of what we've got going on here. So I'm going to draw a line through the arrow to visually divide that I have the left side and the right side. And then on the left over here, I'm going to list the different elements that I have. So I've got sulfur and oxygen. And then under each of these reactants and products, I'm going to write down how many atoms of those elements are in there. So in sulfur dioxide, SO2, there's 1 sulfur and there are 2 oxygens. Over here in O2, there are 0 sulfurs and there are 2 oxygens. And then over on the right, this has 1 sulfur and 3 oxygens. It's kind of messy. It's a little easier to do on lined notebook paper, but so let's start with the sulfur. We have 1 sulfur on the left and 1 sulfur on the right. So that one's balanced. Then we move on to the oxygen. How many oxygen atoms are on the left side? 4. 2 plus 2. And on the right side we have 3. That's not the same. Okay? Now, you can do crazy math and think a lot about this, or you can say, well, I don't have enough oxygens on the right side. I need to put more. The only way you can put more is to add another SO3 molecule. So if I put a 2 in front of this, it's a crazy looking 2. Now that changes everything underneath it, all those numbers. Now I have 2 sulfurs and I have 6 oxygens. And you may be saying, yeah, but that's overkill. You added too many oxygens. Just wait. Just wait. So now I've upped the oxygen on the right side, but I changed the sulfur that I had already balanced, didn't I? So we need to go back and fix the sulfur and then continue working on the oxygen. Now we have 2 sulfurs on the right and only 1 on the left. So we're going to have to put a 2 over here, and that's going to change these guys. Okay? So whatever numbers you had down there, now I'm multiplying by 2. I'm going to multiply all those numbers by 2 and write the new numbers down. Now I look at my sulfurs, 2 on the left, 2 on the right. Now I'm going to go back and look at the oxygens. How many oxygens are on the left? 6. And how many are on the right? Cool. 6. It took care of itself. It'll do that a lot. Okay? Do you see the process there? So there's our balanced chemical equation. Let's do another one. Write a balanced equation for the reaction between aqueous hydrochloric acid and solid manganese 4 oxide to form aqueous manganese 2 chloride, liquid water, and chlorine gas. This sounds like a shopping list or something, or Doofenshmirtz or something. Again, we have to form that's dividing our things here. We've got hydrochloric acid, and we've got manganese 4 oxide. We've got manganese 2 chloride. We've got water, and we've got chlorine. We need formulas for all of these guys. So hydrochloric acid, we learned how to do acids. What kind of an acid is that? Is that a binary acid or an oxyacid? It's a binary acid. We can tell that because it starts with H. No, it starts with hydro. They all start with H. It starts with hydro. So it's just hydrogen and chlorine. So the formula for hydrochloric acid is HCl. And it says that that's aqueous, so I'm going to put AQ in parentheses. And that reacts with solid manganese 4 oxide. It's another one of those ionic compounds. So I'm going to do some scribbling off to the side here. Manganese is Mn, and the 4 tells me it's a 4 plus charge. 4 plus. And oxide. Oxygen has a 2 minus charge. So we look at those charges. They're not the same. And so we learned that we could do crisscross with that, right? Then we would end up with Mn2O4. This is one of the small percentage of compounds where if you do crisscross and don't think about it, you're going to get yourself in trouble. Is 2 to 4 the lowest ratio that we could have? No. This is MnO2. Okay? Because 2 to 4 is the same as 1 to 2. We can also look at these guys and say, well, if I have a plus 4 here and a minus 2 there, I'm going to need 2 of these guys to balance out the charge. So I'm not going to spend too much time on that. So this is MnO2, and it said that was a solid. And this forms aqueous manganese 2 chloride. Well, let's see, I need some more scribbling. So manganese 2, Mn2 plus, chloride is minus 1. Not the same, crisscross works on this one, MnCl2. So I'm making manganese 2 chloride, and that was aqueous. Liquid water, what's the formula for water? H2O. Gotta memorize that one. And chlorine gas. Is chlorine a diatomic element? Horses need oats for clear brown eyes. Clear, Cl, chlorine, 2. And a G. Now, you'll appreciate this. I won't give you questions in this form on an exam to balance, because this is mixing a whole bunch of stuff together. So I won't do this to you on an exam. But I think they do it to you in the homework, and it's good practice. Now we need to balance this, and here it's helpful to do that tallying thing because we've got these elements appearing all over the place. So I'm going to draw a line here. And I'm just going to go left to right and write down the different elements I have. I have hydrogen, I have chlorine, I have manganese, and I have oxygen. And then I'm going to take inventory. In HCl, I have 1 hydrogen and 1 chlorine and 0 manganese and 0 oxygen. Over here in MnO2, I have 0 hydrogens, 0 chlorines, 1 manganese, 2 oxygens. MnCl2, 0 hydrogens, 2 chlorines, 1 manganese, and 0 oxygens. In hydrogen, in water, I have 2 hydrogens, 0 chlorines, 0 manganese, 1 oxygen. And in chlorine, I have 0 hydrogens, 2 chlorines, 0 manganese, and 0 oxygens. Those look funny. Kind of looks like zoo if you read down. So I took inventory. What do I have? I really think most of the time it works out well to just kind of go left to right. So let's look at the hydrogens. Are the hydrogens balanced? No. We have 1 on the left and 2 on the right. So we can fix that by putting a 2 in front of the HCl. When we put that coefficient in there, then we have to change the numbers below. We have to multiply everything by that coefficient. The zeros won't change. 0 times 2 is still 0. So we fix the hydrogens, 2 on the left, 2 on the right. Let's look at the chlorines. Are those balanced? No. But the chlorine over on the right is all by itself, isn't it? So maybe that's one we should leave for the end. So let's skip him. Manganese. 1 on the left, 1 on the right. Well, that's working out okay. And then oxygen. 2 on the left, 1 on the right. So we're going to have to do something about that. We can't take away from the left, so we have to add to the right. So if we put a 2 in front of the water, then we'll get 2 oxygens. But we also changed the hydrogens to 4. We changed hydrogen. That's something we already balanced. So now we need to go back and fix the hydrogen because it's not balanced anymore. So we've got 2 hydrogens on the left. We need to make that 4. So we're going to get rid of this 2 that we put in there, and we're going to put a 4 there. That's going to make this a 4 and that a 4. That changes the chlorine, but we decided to wait on the chlorines till the end. So now we look at this. We've got 4 hydrogens on the left, 4 on the right. The chlorines, well, let's see what they're up to. 4 chlorines on the left. How many on the right? 4. Oh, nice. And manganese, 1 and 1. And oxygen, 2 and 2. So we're done. That's balanced. The check is to go through and look at it again. So over here, I'm going to say, okay, well, here I've got this 4. I've got 4 hydrogens. I'm going to go look over here. 2 times 2, that's 4 hydrogens. Okay. 4 chlorines, none over here. 2 there and 2 there, that's 4. 1 manganese and 1 manganese, so that's okay. Here I've got 2 oxygens and 2 times 1, 2 oxygens over there, unbalanced. So if you want to use your little tally at the bottom, do that, but then when you check it, go up and actually look at the equation. Any questions about that one? Isn't that fun? Here's another one. Write a balanced equation for the reaction between liquid benzene, they give you the formula because we haven't taught you that name yet, and gaseous oxygen to form carbon dioxide and liquid water. So first we write all the formulas. So liquid benzene, C6H6, in parentheses, an L, that's a mess, that's too messy. L plus oxygen. We've done oxygen before. He's a diatomic element. The 7 diatomic element thing is what you need to remember when you have an atom, when you have an element that's alone. Okay? Hydrogen is also a diatomic element, and there it is in benzene, but it's with another atom, and so we don't need to worry about it. So this forms carbon dioxide, CO2, carbon dioxide, carbon 2 oxygens. And that's well, they didn't tell us what the state was. Do we know what the state of carbon dioxide is? Probably at room temperature. Is it a solid? Do you know what carbon dioxide is?
Gas.
It's a gas. Because when you breathe out, you're breathing out carbon dioxide. Hopefully there aren't chunks coming out when you're breathing. It's not a solid. and liquid water. So H2O, liquid. And now we're going to tally these things up. If you can do these without writing all this stuff underneath, you just go right ahead. I'm just doing this for the people that just need a little more help. C, H, and O is what we have here. C, H, and O. In this first one, there's 6 carbons and 6 hydrogens and no oxygens. In O2, there's no carbon, there's no hydrogen, and there's 2 oxygens. Then I come over here, I've got 1 carbon, no hydrogens, and 2 oxygens. And over here, no carbons, 2 hydrogens, and 1 oxygen. Everybody okay with that? That's understanding what the formula is telling us. Then we look at this, and again we see oxygen by itself, so we're probably going to leave that one till the end, and it's on the bottom of the list, so we were going to leave it to the end anyway. So C6, we've got 6 carbons on the left, we only have 1 on the right. How do we make more carbons on the right? We need to put a prefix in front of the CO2, because that's the only one, not a prefix, a coefficient. We need to put a 6 here, so that we can have 6 carbons. So that's going to multiply all these guys. This is going to be 6. H's are still 0 there, and this is going to be 12. 6 carbons on one side, 6 carbons on the other side. With the hydrogens, I have 6 hydrogens on the left, and I only have 2 hydrogens on the right. What do I need to multiply 2 by to get 6? 3. So if I multiply that, put 3 of those, I still have 0 carbons. Now I have 6 hydrogens and I have 3 oxygens. When you put a coefficient in front of a formula, you have to change all the numbers underneath because it affects everything except the ones that are zeros. So our carbons are balanced, our hydrogens are balanced, and now we need to fix the oxygens. How many oxygen atoms are on the right side of the arrow? 15, right? 12 plus 3 is 15. On the left side, we see that the oxygens are coming in pairs. You can't just buy 1, you get 2. How do we get 15 from pairs? Well, we see that this is an odd-even problem. So for those of you who like fractions, I'll tell you the fraction method real quick, and then I'll show everybody else the other way. Is there a fraction that we could multiply that would give us 15 oxygens? We could multiply by 15 halves, right? 15 halves times 2 would give us 15. So that's how you can end up with fractions in your equation. So if you put it in here. If you put 15 halves in here, 15 halves times the 2 oxygen is going to give us the 15 oxygen atoms. And then we'd have to clear the fraction by multiplying everything by 2. So those of you that get that will have gotten it by now, and then I'm going to show you the other way. So we recognize that we have an even number on the left side. The oxygens are coming in pairs. On the right side, we need an odd number, and that's not going to work out. If we double everything, the odd number magically turns into an even number, and the problem goes away. So what we're going to do is we're going to multiply everything we've done so far by 2. So we're going to put a 2 here, and that changes this, and that changes this. We're going to leave that oxygen alone because that's what we're trying to figure out. We're going to change this to a 12, which gives us 12 carbons and 24 oxygens. Don't be afraid that that's too large of a number. It's okay. And over here we need to double this and make that 6, and that makes this 6 12, and that makes this to be 6. Okay? See that? I just doubled everything except the one we're trying to fix at the end there. Now how many oxygens do we need on the right side? 24 plus 6 equals 30. 30 is an even number. Yay! How many pairs to get 30? 15. So if we put a 15 in here, we're going to be good. So if you're balancing and you come up with an odd even issue like that, double everything, and then it'll go away. Any questions? You're going to have so much fun on this homework.